Okay, so let me know if you can see the screen. Hello.
Yeah, we can see.
Yes.
Okay, so I think this is where we stopped last time. We saw that when we design with Verilog HDL, we can target this is we can easily migrate or port it to a different device. The design could be ported to different FPGAs, Xilinx FPGA, Intel FPGA, or we can also use the same Verilog design to convert it to ASIC, for that matter. So, any questions on anything before we proceed?
No.
Okay, so the advantages of HDL compared to schematic tools is HDL is more universal. It's a language, so we can use the language. Since it's a language, we can, and it's an open language. It's a IEEE standard, which is open for all the engineering community. So it can be used. Schematic tools, whenever even now, schematic tools are used to a certain extent for some very small part of the designs. They are mostly proprietary. There are some open source tools, but they are not as good. There are some proprietary tools which are sold by commercially sold by companies. So language is always better than proprietary tools. It promotes design reuse, and it promotes integration of third party designs or IP. So IP stands for intellectual property codes. Basically, what that is, it's a small design. IP core is a small design which you can buy or license from some third party company. So nowadays, the way designs work in the industry is nobody designs everything from scratch, and nobody designs the entire chip by themselves. Normally, what companies end up doing or teams end up doing is they would license IP cores from some other third party company and integrate that IP core as a part of their design, right? So if you have this, if you want an analogy based on embedded systems, so imagine if you are buying libraries of different functions from different companies or some other company, and you are using those functions as a part of your program. Same concept is used here. IP, intellectual property core, is a small design or even a big design, depending on what it is, could be licensed from some other company and then use it. You can use it as a part of your own design. That's how third party designs or IP cores are used, and that is what it means by design reuse. So I can, for example, I can there are some companies, all they do is develop IP cores and sell it to other companies. So I can design a let's say I have designed an encryption core, right? Somebody wants to use encryption, so and they don't want to spend time, they don't have time, or they don't want to spend time developing this encryption code. So let's say I'm running a company, I have designed the encryption code, and somebody else wants to use that, I will license it to them, and they will use. So depending on, there are two types of licensing schemes normally. The source code is delivered, or it is delivered as a hard IP. That means a netlist is delivered, so not the Verilog source code, but you can use it without the code also. So I can deliver the Verilog code, or I can deliver it in a binary format. But I can take it from somebody else, or I will sell it to somebody else, and they will use my IP code for encryption algorithm. So this promotes design reuse. What happens is, due to this, the overall design cycle or the overall time required to design a chip is drastically cut down. Since you're taking a chunk of your design from somebody else and just integrating it in your design. That is what Verilog offers you. Something to remember is HDL is not a programming language. So since a lot of people come from C background or some other programming, software programming background, you have to remember that Verilog is a HDL, hardware description language, and it is not a programming language. We have already seen the main differences between any programming language. For example, C language and Verilog language. Do you remember the two key differences that you get? Key differences between, let's say, C language, programming language, and Verilog language that we saw. Can you recall that?
Yes.
Yeah, please, Rolling.
It's
Uh,
parallel.
yeah, go ahead.
It's parallel and sequential. Programming languages are sequential, whereas HDL is parallel.
Yes, concurrency is very important, or parallel execution is very important. That is not really offered by programming languages. The second one,
I don't remember the second one.
okay, anybody else? Second difference, key difference. No, okay. So timing control. We talked about timing control. So using clocks, we'll be using clock throughout the design for our HDL or hardware design, and we can control now. Let's say we saw this when we saw sequential logic in digital logic design, that flip flop is the basic sequential logic component, and we will use flip flops to develop registers, shift registers, counters, memories, etc. And flip flops are used along with edge triggered. They are edge triggered flip flops working with respect to positive or negative edge of clock. So every clock edge we can control the circuit as required. That will give us timing control at a very fine level, which is not possible in C programming language or any other programming language. So the timing control and parallel execution are the two key differences that you will find in Verilog, which will not be available in the programming language. And obviously, sequential and parallel execution, C language or any programming language will go from top to bottom sequentially, one line after another line. In case of Verilog, that's not how it works because it has to support parallel hardware. So parallel hardware design is supported, and we'll see how it works. But that is supported as a part of the language. Second thing to remember is HDL, a Verilog language or HDL is not, it is abstract compared to schematic designs or CMOS transistors. So it's a language, and I can design a circuit using language, which is better compared to CMOS based design or schematic gate based design. But it is not also highly abstract, where I can just type a line like this. This is basically a DSP algorithm, a filter or a signal processing algorithm. I cannot just write this line in Verilog and expect Verilog to implement a digital filter or a DSP component algorithm for me. So that happens in this kind of things happens in system level languages. So if we are anybody have used MATLAB here, they would know this kind of thing can be implemented with MATLAB to a much better level, or any other system level language where filters and some other components and other algorithms can be implemented at a much easier level compared to Verilog. So there, if you remember, I talked about going to system level languages or higher level languages. So it is right now there is work going on to develop Verilog even further. System Verilog is one candidate, and there are some other things also in the pipeline. People are working on those languages where this kind of thing will be allowed. So right now I can implement this in Verilog, but I cannot do it like this. I have to break it down into a block diagram kind of thing. I have to develop it part by part, and then it will implement the signal processing algorithm for me. So I can develop this in Verilog, but I cannot just write this line and expect a Verilog synthesis tool or other tools to implement a filter for me or a signal processing algorithm for me. So it's getting there, but it's not that level of abstraction is still not supported in HDL. It's better than CMOS transistor design. It is better than schematic design, but it is not. It lacks somewhere in system level implementation when you compare this Verilog to, let's say, MATLAB or some other system level languages, System C even for that matter. So uh, key differences. There are differences between programming languages and Verilog. There is a difference between Verilog and system level languages. So you have to keep that in mind when you do your design. Verilog and VHDL became live as simulation and modeling tools. So Verilog and even VHDL, when it was invented a while ago, it became as they started out as simulation tool, means modeling tools. Create a software model. Uh, at that time, schematic method was used for design. So Verilog and VHDL languages were used to create equivalent software models, and the model output was tested with respect to schematic output. If it matched, then you said, yeah, my design seems to be okay. So initially they were used only for modeling purpose. So creating a software model. Then later on, hardware synthesis was developed during 1990s. At that point, the entire game changed. So I can convert Verilog using synthesis tools or software. I can convert Verilog to netlist, gate level netlist, and then carry it forward in the backend part of my design. So that was the key part that was developed in 1990s. But the thing to remember is we have to use a subset of Verilog and certain coding styles or design styles to allow synthesis tool to infer correct hardware. What this means is synthesis tool or synthesis software, Verilog file is an input file. It will read the Verilog file, and based on your Verilog description, then the synthesis tool will implement or infer. Infer means based on your Verilog, it will generate certain gate netlist and certain designs for you. So we have to, first of all, only part of Verilog is synthesizable. So only part of that is synthesizable, and we have to understand a little bit better how synthesis tools work, what kind of Verilog to write. So synthesis, for example, if you want to implement a counter, now we have to write the Verilog in such a way that the synthesis tool understands that this Verilog code is meant to implement a counter. Then it will, based on that Verilog code, it will implement a counter in hardware. So we have to keep this in mind. So this is what that means. This is entire Verilog language. Out of this is synthesizable Verilog, which is can be used to implement hardware on a FPGA or a ASIC device. Rest of the language is meant only for simulation purpose. So there is still a lot of language which is only meant for simulation. Part of the language is meant can be synthesized to hardware, and this ratio is around 60-40. 40% is around synthesizable part of the language is 40%, the rest is around 60%. And it is improving day by day, so more and more part of the languages is synthesizable. Probably it could be around 50-50 also now. So but there is significant part of Verilog which is still used only for simulation purpose, for verification purpose, not for design purpose. Any questions here?
No.
And this is where we'll focus. So there are certain learning hurdles that you might face to write. So what are some of the hurdles? You may try to write HDL code as it will be eventually be executed by some processor. So this is coming from a software background, right? When you write some software, you write a software program, you'll compile it, you link it, you'll generate some code which will get you'll generate a hex code which will get implemented on a processor somewhere, or which will get executed on a hardware. You take embedded systems, it will implement those instructions or execute those instructions on a processor. That's not how HDL code works. We have seen the entire flow. We start out with Verilog code, we verify it, then we synthesize it, follow the backend process, then we generate something called a bit file. That bit file is a programming file, which is then used to program the FPGA, and the same thing goes on for ASICs. So the entire chip is can be designed as per your logic. There is no inbuilt processor by default. You can have a processor, but there is nothing by default. The entire chip is programmable, or in case of ASICs, the entire chip can be designed as per your logic. Processor may or may not be present. In case of embedded systems or in case of software, you're trying to run a software application, ultimately it will work on a processor somewhere. So that's a key difference there. Code is written sequentially like a program, but you are simply writing descriptions of various hardware entities in your system. Again, the same issue is sequential execution versus parallel execution, and we'll see how to describe these things or write this in Verilog. So what is Verilog? Verilog is really a hardware description language. We're describing the hardware. We are not programming the hardware. Why use Verilog? Right, as it started out around, if you remember, I said that when it started out, most of US or North America for that matter, which is US and Canada, was pro Verilog. Europe was pro VHDL till a long time. Later on, you had companies from US opening branches in UK and other parts of Europe. Now you had a lot of companies have opened branches in India. So now it's all a mixture, and Verilog is much more preferred language in the industry today compared to VHDL. VHDL is also used right now in the industry, but it has fallen slightly behind. VHDL is more preferred for academic purpose. When you go to universities around the world, they mostly prefer VHDL even now. Could be a reason why Verilog has become more popular is syntax is very similar to C language and it is simple to learn. VHDL is something called a tightly typed language. So there are more strict rules when using VHDL compared to Verilog. Verilog is much more flexible and the syntax is somewhat similar to C language. So coming from a C background, which a lot of people have, it's easier to learn Verilog. So we saw some of this. Why use a HDL? We want to design complex circuits and very quickly. So we can use HDL designs, use synthesis tools and backend tools and quickly implement designs, very complex designs. We cannot use a general purpose language because the support for timing and concurrency is not there. This bit level behavior was also not present, but now embedded systems allows you to control bit level and other things. C++, on the other hand, or any object-oriented language, use the concept of structure and instantiation of modules. So if you have done object-oriented programming, there is a class and there is an instance, or a class and object. So the same concept is used in Verilog. You can have a module and you can have an instance of the module, where you can replicate that module or copy that module or create copies of that module and make connections as required. So that's called instantiation. We'll see later on what this means. So some of this was supported by object-oriented programming. Some of this was supported by programming languages, timing, concurrency. All of this is supported by Verilog. Structure and instantiation, bit level control, bit level behavior, timing control using clocks, concurrency for parallel logic execution. All of this is supported by Verilog hardware language. Verilog versus VHDL, we just saw that Verilog is more popular right now. It's just the way it works. So, how does the modern project methodology work for any hardware design? Right. So let's see this slide. Now, this is FPGA oriented. So, just this is what you will write in Verilog. So, this is your Verilog code. Just before Verilog, you will have a design specification document which talks about what needs to be implemented. Based on that design specification document, you will write Verilog code. And this is the design cycle that we're looking at. After writing the Verilog code, the functional verification aspect will happen here. Once it is verified, this Verilog code will be synthesized, where the Verilog code will be converted to gate level netlist. Now this gate level netlist will consist of generic gates, basic gates, AND gate, OR gate, NAND gate, NOR gate, etc. That netlist then will be mapped to technology specific components. When I mean by technology specific components, let's say I'm using a Xilinx FPGA. Now under Xilinx FPGAs, there are multiple families and series of FPGA. So let's say Spartan 6, Spartan 7, Vertex 6, Vertex 7, etc. So based on which FPGA you're choosing, there will be something called a technology library, which will have its own components. So this generic netlist will be converted to technology specific netlist with its own components from the library. Then these components will be placed and routed. It will be placed throughout the chip, and routing means all the interconnections will be done. So this Verilog code will work on the FPGA chip in this format. And this chip is a part of PCB, which is a part of a product. So this Verilog code will work as a part of a product. This is called the modern project methodology or design methodology that you will use for FPGA design or even ASIC design. Doesn't matter. It's the same concept. Okay, do you want to note this down, this slide?
Yes, just a second.
Yeah. Let's see if I can pull this down a little bit. Yeah, okay.
Okay, it's okay now. I'm good.
Okay. So any questions on this slide or in general this methodology anywhere? Because this is what you'll be using for all designs.
No.
Nope. Okay. Yeah. So learning Verilog, you need some background in digital logic design. So which you already have, and any programming that you might have done earlier will help you understand the concepts better. So a little bit history about Verilog. So Verilog was actually invented, or uh, uh, it was formulated by a company. It was a private company who invented Verilog called Gateway Design Automation long back in 80s, and they developed their own simulator in mid 80s, called Verilog itself. It was very popular and it sold a lot during that time. In 80s, late 80s, early 90s, Synopsys was a company which is now the number one India company. It developed synthesis tools to convert Verilog to gate level netlist. And Cadence Design Systems acquired Gateway in late 80s, early 90s. At that
I
time,
think the Fahad is not on mute, so is interfering with the.
okay, can you mute?
Sorry for that.
Yes. Yeah. Okay. So this language Verilog was invented by a private company, and it was they developed their own simulator software and sold a lot of them. Synthesis was developed by Synopsys in late 80s, early 90s. Gateway Design Automation was acquired by Cadence Design Systems in late 80s. It was still a proprietary language at that time, so it was not released to the community, engineering community. That was in mid 90s, early 90s actually, that it was released and to the engineering community, and it became a IEEE standard. And once it became a IEEE standard, then we had something called LRM, which is a language reference manual that we have for all languages. Every language has its own language reference manual, and the language is based on this. So it became a IEEE standard in around early 90s, mid 90s, and it's been a IEEE standard ever since that. IEEE standard, the advantage is that now there is a committee of people, engineers, scientists, people in the industry, people from the academia, all over the world, who are part of this committee, who look after this language. Now, this number 1364 is given for Verilog. So IEEE standard 1364 is Verilog, and it's a group. Working group means it's a committee, group of people who are involved from all over the world, and they improvise or they enhance the language every few years, around 5 years or so. Every 5 years there will be a new something new that has come up in the language. Some additional part is we saw the synthesizable subset and simulation part of the language. So every few years the synthesizable part will increase. More percentage of the language can be synthesized. There will be some new additions to the language, and all of this you can go Google this IEEE 1364 standard. You can go to the site and download this LRM and Verilog related details. And every few years a new version of Verilog comes out, and depending on which software you are using, they'll tell you that Verilog standard number so and so is supported with this software. So every few years a new version of the language comes out. That's a little bit of history about Verilog. So what we will see now, we will start looking at Verilog in detail, syntax in detail. So what we'll see is mainly there are two types of modeling or design methods in Verilog. One is called RTL modeling. Now this word RTL and behavioral modeling will be used interchangeably. RTL was what was called earlier. RTL stands for Register Transfer Language. RTL sometimes is called HDL, sometimes we call it behavioral modeling. It's all the same thing. RTL was what was called initially, then it was now we call it behavioral modeling, or very rarely we will call it HDL. HDL and RTL is the same thing. It's a language based on description of the language. And that is one method to design circuits, digital circuits in Verilog. And the second method is structural modeling. So like schematic design. Now in schematic design, what we did was we took a few gates, connected inputs and outputs of each gate to the appropriate connections. So we can use language to create that structure in Verilog. So that's called structural modeling. So that is still done for very mission critical, very when there are very critical designs. We might have to do a little bit structural modeling for that purpose, but very rarely you use structural modeling. But it is still there as a part of the language. So you can design your digital circuits mainly using these two methods: behavioral modeling or RTL modeling, and the second method is structural modeling. Now, what are the digital circuits that we are going to design? We already saw some of that in the basics. Combinational circuits, basic gates, basic combinational circuits, multiplexer, demultiplexer, encoders, decoders, adder, subtractor, etc. Then we can design sequential circuits, basic flip-flops, registers, shift registers, up-down counters, memories, could be RAM or ROM. RAMs can be of different sizes, etc. Then we could design FSMs, finite state machines. FSMs internally can be a combination of combinatorial circuit and sequential circuit, both put together. All of this can be designed using Verilog. And how to do that, we'll see some examples as we go forward. Yeah, so we saw that this concurrency and timing control is supported, structural and behavioral modeling is supported. We also saw that at the most basic level, this is the different level of abstraction that we saw in one of the first presentations. Switch is a transistor level, CMOS level, then gate level, behavioral Verilog, and algorithmic level, which is a system level language, which is still being developed. So we don't work on CMOS level. We hardly work on gate level designs, which is structural level designs. This is where we will work, behavioral RTL, to define the behavior of our system using data flow concepts, control signals, storage elements, which are memories or registers, clocks, etc. Algorithmic level is still not used. That is a different part of the different languages which is being developed. So this is where we'll operate at a maximum level. Structural descriptions is netlist using primitive gates. Primitive gates means basic gates and switches if required. Continuous assignment statements are also part of that. We'll see what this means. Behavioral description is a functional description of the design, any timing controls and concurrency specifications. Procedural blocks is very critical, always an initial block. These are part of the behavioral modeling. Any registers, latches, etc. So when you compare Verilog to a programming language like C language, so programming language plus timing control plus concurrency will give you hardware description language. The key part is all procedural statements. Procedural statements are behavioral statements in Verilog. For example, always block. Always, the way it works is always at, now there is a bracket. In the bracket, you can have a signal name or a bunch of signals. This is called a sensitivity list inside the bracket. That means that, let's say, always at temp1, temp2, temp3. This is what I have. That means this always block is dependent on temp1 signal, temp2 signal, and temp3 signal. Any change in temp1 signal or temp2 signal or temp3 signal will trigger the execution of this always block. It can have one or multiple signals. It can also be dependent on clock, edge of the clock, pause edge of the clock, or neg edge of the clock. So you can have any of those in the sensitivity list. So this is called, anything in the bracket is called sensitivity list. This always block is sensitive to those signals. Any change in those signal values will trigger the always block. And internally, whatever logic is described inside the always block will be executed. What can we have inside the always block? We can have the control statements like if then else. We can have loops like for loops or while loops. We can have case statements. Now these case statements are very important and used for FSM design. We'll see how that is done. But case statement is the key syntax or the key construct that we'll use for FSM designs. And you can have some other combinational logic part also. And you have to decide what is done behaviorally and done what is done structurally. Most of the time you use behavioral modeling methods. Now a simple example. Inside the always block, always at activation list or sensitivity list means one or more signals can be part of the always block. Begin. Every always block should have a begin and end. That is like the curly braces that you use in C language. So this is begin for the always block and end for the always block. If x equal to y, then out equal to in 1, else out equal to in 2. So what is this? This is a comparator in hardware. We are checking if x is equal to y. Equal to two signs means we are checking if x is equal to y. If x is equal to y, out the signal gets in one value, else out signal gets in two value. End the always block. So this is a simple comparator that we have. This Verilog code will generate a comparator in hardware for us after synthesis. Delays can be used in always block. Now suppose you want to wait 10 delta cycles. Now we'll not talk about, or let's say 10 clock cycles to make it simple. After an input changes, wait for 10 clock cycles, then check to see if phi signal is equal to 1 and then update the output. So this is what is given to us. And we want to write a Verilog code for this. So what it will look like, always at phi or in. Now this is the sensitivity list. Phi signal or in signal, any change in this, any of these signal values, the always block is triggered for execution. What is inside the always block? Hash 10. If phi, then out equal to in. Hash 10 will give me a delay of 10 cycles. After that, if phi is equal to 1, if phi is equal to 1, then out equal to in. Or if I write it this way, always at phi or in, again sensitivity list is the same. If phi, now first I'm checking, in this case I waited for 10 cycles and then checked if phi is equal to 1. In the second example, I checked if phi is equal to 1, then waited for 10 cycles, and then out is equal to in. So it is slightly different. So now forget Verilog, just look at the logic and tell me that out equal to in after how many cycles in first case, out equal to in after how many cycles in second case. Just looking at the logic.
10 seconds.
10 cycles in both cases, or first case or second case.
Uh, yeah, in both cases, it will change after 10 seconds.
Okay, any other
I
answer?
think I think in the second cycle it would be 11 because it first checks, then count 10, then it updates.
Yeah, this is immediate, there is no delay here. If phi, there will be no delay to check that. So in that case, how many cycles in first case, how many cycles in second case?
I think 9 and 10. Uh,
9, in which case? First one, second one.
I think the second case because it doesn't. There's no. I mean, it doesn't check the first time,
Okay.
right?
So you're saying this will take 9 cycles, this will take 10 cycles, the first one.
I may be confusing this, but I'm thinking one of them should be less than the other.
Okay, that's the logic. Any other answer?
Is it guaranteed that it will be 5 when after the 10 clock cycles?
Phi, if phi, so checking phi will not take any delay. That is the description given by me. So there is no delay to check phi. Additional delay, I mean. So assume phi is 1, always 1.
Okay.
So phi always
Then
1 means there is no delay in checking for phi.
Well, then they just be gonna be 10, both of them, I think.
yeah.
Right? So it will be 10 in both cases if phi is 1. The only difference is in the first case, I am waiting for 10 cycles and then checking if phi is 1 and then out is equal to in. In the second case, the flow changes. First I'm checking is phi is equal to 1, which is always 1. Then wait for 10 cycles, then out equal to in. So out equal to in after 10 cycles in first case, out equal to in after 10 cycles in second case. So right now, since phi was 1, it was the same thing. It may happen that phi is changing at different times. So you have to understand this as you go forward. The main point is you understand this logic and then go forward. And since phi and in are both part of the sensitivity list, any change in phi signal or any change in signal will trigger this always block. In this case, it's a single line. Whenever you have a single line in the always block, the begin and end is optional. That we saw here, begin and end. It was more than once. This is also considered a single line if and else, but it's a good habit to always use begin and end for always blocks to mark it as a block. Okay, so we saw this delay. Then we have something called initial block. Now, initial block is also a procedural statement. Always block is one example of procedural statement. Initial block is another example of procedural statement, but there is a difference that it can be used only once. It does not need activation list. Like always block always will need some activation list, some signals in the activation list or sensitivity list. Initial block will not need any signals. It will run just once when the simulation start in case of simulation, and it will run once when the hardware is started in case of hardware design. So earlier it was not synthesizable, now it is synthesizable. So now this is how initial block works. Now when you take hardware, let's forget simulation because we want to implement hardware. So it will run once. Any logic inside the initial block will run once when the hardware starts. So what can I use this initial block for? Why is it necessary? If it is necessary, what kind of logic can I put into it? Because all it does it just runs once and stop there. Whereas the always block will always work on continuously. Initial block will run once and stop. That's how it works.
Initializing the initial conditions of the block or something.
We have to be more specific from a hardware perspective.
Defining certain signals
Defining certain signals.
like the
More
wires and
like the word, sorry.
the wires, the resistors, those kind of blocks, defining them
Why would you need that? Let us step back one bit and ask us why do we need to do that?
to be able to use them in the later, like in the always block.
Yes, but why do you need to do that?
I think the initial block should be like a definition of the circuit, like what the circuit is, and then so the other part that you talked about, where you do the actual working of the circuit. So let's say you have an adder,
Mhm.
then the always part is just defining what the circuit should do. Like if one and one, then output should be one. But then I think the initial block should define the actual circuit, like this is the adder, and then like the always place define the behavior of the adder, how the adder should behave. I'm just thinking that.
Yeah, just to clarify, that can happen as a part of the always block. So we don't need to do that in initial block. Whenever this always part, now let's say you have an adder in the always block, it will be implemented when the synthesis tool will see this. If it's an adder, it will implement it as an adder. You don't need to declare it separately again in the initial block. So that is not required. So that we don't need to do that again in the initial block. Since you are coming from embedded background, Brolin, can you think about something else?
What about if we say they are like the variables? For example, in the always place, you say x is equals to y, but we still don't know what x is. So would we say in the initial block is where we write like the variables and show how they are connected, like maybe say these are inputs and these are outputs.
That also can be done as a part of the port declarations that we'll see later on. So that is what you're talking about is input output declarations are done somewhere else, not in the initial block. So we are talking
Okay.
purely about logic here, purely logic.
Yes, so initial block we use in test benches to initiate the values to the registers and signals. So if we do
Yes,
not define the initiation, if we do not do the initiation, then the values will be Z or X. So we need to do that in a test
okay,
bench.
but now we are talking about hardware. So test when you talk about test benches, it is only meant for simulation purpose. Can
Yep.
you apply this concept to hardware?
I don't think initial.
Initial block can be synthesized. So all that logic can go into hardware.
Okay.
Earlier it was not possible till many years ago.
Mhm.
Now it is possible. So all
So So what if you want to put it like a function that you will keep on repeating at some other point, like it's a function that you may want to reuse even in another project. So you put it, or so many times in the, it's a function that you can use so many times in the program. So you just want to call it, with the initial. So
no,
you
no,
put it first in the initial block.
no. The initial
Okay.
block cannot be reused by some other design. So that logic is only local to that design. So we cannot reuse. If you want to reuse, it can be done, but it has to be done some other way, not through the initial block. Initial block will be local to that design, so the logic declared will be local, restricted locally to that design. So now let me ask you a question. Now I'm sure you have used embedded boards before, or some of you might have used FPGA boards before, or some other boards. When you turn on the board, what happens? You power up the board, what happens? Something happens, right?
Well, it goes through the reset, the reset sequence or handler.
So just take some example of a reset sequence. Let's say there are four
Sorry?
LEDs. Let's say we'll take example of a reset sequence. Let's say there are four LEDs. The LEDs will be, let's say, turning on one after another and then stop. Maybe that is a reset sequence. Or your power LED will go on. Or if there is a LCD on the board somewhere, it will display some message, right?
Yes.
From memory after the reset, like after the vector
So,
table initial.
so how does that work? When you power, and you don't have to apply reset for that. You power up the board and it shows you that. Some
Yeah,
LEDs will
it
glow, some
vector
message will
table.
be displayed. How does that work?
At after a certain time in the vector table, it goes to the main of the program and starts executing from there. The program counter.
Main will happen later on if you're comparing it to an embedded program. But on reset,
Yeah, that's
on power up, basically.
yeah. Yeah, so on embedded I know it'll first go to the BIOS, like the the code written in the ROM that helps the if let's say it's the microprocessor, initialize all its peripherals and all other stuff that it needs to start up.
Exactly. So there is a ROM built in on the board, on the embedded board. It will transfer that program to the hardware and initialize the peripherals, which LEDs could be one of the peripheral, LCD could be one of the peripherals, and other devices. Correct? So that
Yes.
sequence, that routine of transferring the ROM contents to the initializing the peripheral can go as a part of the initial block logic. Do you agree?
Oh, yeah. Yeah, it makes sense now. Okay.
Let's say there is a LCD display on your board. Normally, when you power up the board, the LCD will show you the name of the company from where you have purchased that board, right? What if I want to display my name when it powers up?
Yes.
How do I do that? So in case of FPGAs using Verilog. So what I do, or let's take in case of embedded. Let's talk about embedded for a minute. I will write my own logic to display my own name or something, or my own custom message on the LCD, reprogram the ROM on the board where it will pick up that ROM contents and transfer and display the appropriate custom message when you power up the board. I can do that. Now the same concept I want to apply to FPGA board where I have to use Verilog as an input language. How do I do that? I put all that logic in the initial block. So when I power up the block or when I apply reset for that matter, let's take a reset. Then I can show all that, let's say a custom message on the LCD board. So that's one thing I can do. Another thing we can use initial block is whenever you have memories in the design, big memories in the design. Somebody mentioned this. We always have to initialize the registers. Internal memory are registers. Internal they are registers. So the memory has to be initialized. All the contents, all the bits of the memory has to be initialized to 0 or 1. So they don't start from Z value or tri-state value. So that's one another thing you can do. So anything that you want to do once when the hardware starts, because ultimately this will generate hardware for you. You can put all that logic in the initial block. That has to run once. Okay.
Okay.
And then whatever logic has to continuously execute can be put in always block. And you can have one or multiple always block. So the way it works is, I think yeah, it is there in the next few slides. So I'll not talk about that right now. We'll see how multiple always block works. So this is how initial block works and the always block works. Any questions on this? No. Okay.
No.
So using Verilog, we can build hierarchical designs or bigger designs. How does that work? Let's say this is how I want. This is a hierarchy that I want to develop. So sub 3 is a sub block under com2 block, component 2. Com1 and com2 are sub blocks under the main top level block called system. So what I do is, this is the hierarchy of the design. Our system is top level com1, com2. Under com2 I have sub 3. So each of this, now basic thing in Verilog is module. So everything will be its own module, a separate module. So we will have a module for sub 3, we will have a module for com2, we will have a module for comp1, and we'll have a module for system. So what I can do is I can instantiate, that's a term used, I can instantiate sub 3 under comp2. When I do that, I create a copy of sub 3 under comp2 and make the connections. Then I will instantiate this combined module under system, and I will instantiate comp1 under system and make connections between system and comp1 and system and comp2. So this is how I will create this hierarchical design. Sub block under this block, these two blocks under system top level block, and system will be the top level entity or top level where we are using the input output pins coming from this. So hierarchical methodology, hierarchical designs can be done top down or bottom up. What that means is I can start with the lower level modules first, then develop the higher level module, then the top level module. Or sometimes it works the other way around. In today's world, you have big companies who have branches all over the world. So you will have teams all over the world. So let's say there is a company, multinational company, who have offices, two offices in US, one in Europe, one in India. So four teams will be assigned different blocks of this design. So maybe one team is assigned all these blocks, or one team is assigned macro 1, macro the second team is assigned macro 2, macro 3 is going to the third team, macro 4 is going to the fourth team. And one of the teams, or there is a separate fifth team who is integrating all of this at a top level. That is typically how it works. So hierarchical design can be done bottom up or top down, because all the each block, what it needs to do, how it needs to communicate with different blocks, all of this is part of a design specification document. All of that is documented and written down very clearly with what needs to work, what is the logic for top level, what is the logic for sub block one, the leaf cell, etc., and how they need to communicate with each other. So we can go from top to down or bottom to top, because we are using different teams to create different blocks. So this is how design is done, and verification is done by a completely different team who is not doing design. Whoever does design doesn't do verification or testing. Whoever does verification doesn't do design. The teams are different. So verification team will develop their own software model nowadays using Verilog, or it could be using some other language. You might have come across E language or Vera by Synopsys, or some other languages are also there. System C is still used, System Verilog is used. A separate model will be developed like this design. A separate software model will be developed. The output of that model will be compared to the output of the design. If they match, which is called a monitor, to monitor both sides, the design output matches the verification outputs, you say my design is verified. If the design output doesn't match the verification model output, there is a problem. Then you have to fix the problem wherever it is. So forget the verification for now. The design can be done this way. A hierarchical design can be done bottom up or top down. And this is very common that you will, this is broken down into steps where, and then one member, one engineer of the team might get assigned to develop this block. And then he or she has to write Verilog code for it, a separate test bench for it, verify the block, and then hand it over to the sub block level. That's how hierarchical designs are developed in Verilog, which is extremely common. So everything, as we said, is inside a module. So module is a key part of Verilog. Anything input output ports, as we were talking about right now, initial block, always block, any other declaration in Verilog is inside the module. So module, name of the module, and the input output port list, the local wires, local signals, initial block, always block, end module. Module and end module. So this is the module under which we have all the logic inside Verilog. And we can have separate modules like we were seeing here. Sub 3 will have a separate module, COM 2 will have a separate module, COM 1 will have a separate module, and system will have a separate module. And each module is a separate Verilog file. So one Verilog file, one module. Technically, in one Verilog file, you can have multiple modules, but that's not the guideline how to use it. One Verilog file, it should have only one module. Different modules should be in a different Verilog file. And modules can be interconnected to describe the structure of your digital systems. As we saw here, modules can be interconnected between each other. Module starts with a keyword module and ends with a keyword end module. Module and end module are keywords in Verilog, so I cannot use it anywhere else. And modules have ports for interconnection with other modules. So how do I interconnect them with other modules? Now this interconnection is happening between sub 3 and COM2 and system. How do I do that? I have ports, which is part of the port list. So port list can be input ports or output ports or in-out ports for bidirectional ports. We'll see that. Using those ports, I can connect, let's say, this module to this module, and this module to further some other module. Let's take a simple example, and two input AND gate. Now this is a simple two input AND gate. I0 is one of the inputs, I1 is one of the other inputs, O is representing the output. So what is the Verilog code for this? Module AND2. AND2 is a custom name. So I can name it anything I want, but the name should be synonymous to the logic that you're developing. So this is a two input AND gate, so I call it AND2. Module AND2 bracket I0 comma I1 comma O. This is my port list, out of which I0 and I1, each of them is a single bit input port. Is a single bit port, input port. O is a single bit output port. So I've declared the module, declared the input output ports. Now I want to declare the logic for this. Assign. Now this is a continuous assign statement, which is part of Verilog. Assign O is equal to I0 and I1. Output O gets input I0 and with I1. This will help me when I synthesize an end module. When I synthesize this design, it will give me a two input AND gate. So simple two input AND gates, two inputs, one output. Module is a keyword, end module is a keyword, assign is a keyword, input is a keyword, output is a keyword. What is the name of the module? AND2. Because it's a two input AND gate, I have named it AND2. I0, I1 and O are the port list. Any ports, input and output ports are part of this port list in the brackets. Then you have to declare out of these three ports, I0 and I1 are input ports. Each of them is single bit. O is the output port single bit. And then the logic for this module is assign O is equal to I0 and I1. This statement and I1, I0 and I1 will synthesize this design, this Verilog code to a two input AND gate. So in the netlist, I will get this AND gate. Okay.
What does continuous assignment mean? Like the assign
Yeah,
keyword?
we'll see that. We'll see the how that is different compared to initial block. We can now inside the module I can have assignment. It's a continuous assignment means I0 and I1 is continuously evaluated and output O is updated as per the input value. This continuously works. That's why it is called a continuous assignment. So any change, whatever the current value of AND gate is a combinational logic, right? Basic gate. Combinational logic output is function of inputs. Anytime the input changes, the output will change. Else the output will remain the same. But this is continuously executed like this AND gate in hardware. Any input value, based on this input value and based on the logic of an AND gate, the output will be generated. That is what is replicated in using this Verilog statement.
Okay.
Continuously evaluated, continuously generated output. But the syntax is like this. You have to say assign O is equal to I0 and I1.
Are modules used like functions in the always blocks?
Yeah, we'll see that. We can use that, but we don't want to use functions for such a small thing. Functions are used for much more complex logic that can be replicated. And like assign statements, we'll have always block in the module and we'll see how that works. On this slide, any question we can take that. No? Okay. So now we saw that we can build hierarchical or bigger designs using basic blocks. So now using this two input AND gate, I am going to generate a three input AND gate. For that I need two such AND gates. And this is how I will build a three input AND gate. This first inputs of the three input AND gate is coming to the first gate. And the output of this AND gate goes to the input of the second AND gate. And the third input of this AND three gate, the three input AND gate comes here. This is the final output that goes out. So what is the Verilog code for this module AND3? Now why AND3? Because it's a three input AND gate. So I should name it appropriately. Module AND3, this is the port list, I0, I1, I2, O, out of which I0, I1 and I2, each of them is a single bit input port. O is a single bit output port. There is a wire called temp. I have to declare a local wire called temp, which is going to be connecting the output of this gate to the input of the second gate. Now these two input AND gates, I need two copies of them. So I am going to instantiate this two input AND gates two times. And 2 and 2. Now these two copies are differentiated. These are the label. This is the instance label for first instantiation. This is the instance label for second instantiation because I have to differentiate it. These are two copies. First is called A0, second is called A1. Dot I0 goes to I0. So dot I0 dot I0 dot I1 and dot O are input and output ports of the two input AND gate. And in the bracket I0, in the bracket I1, in the bracket temp, in the bracket I2, in the bracket O, these are local signals at AND3 level. Dot I0 of the two input AND gate goes to I0 of the AND3. Dot I0 of AND gate AND2 goes to I0 of this local input port here. Dot I1 means I1 port of AND2 will go to I1 port here. Dot O means this is the output of the first AND gate for this second two input AND gate. Dot O goes to temp. Dot O, which is the output of the first AND gate here, goes to temp. Now I instantiate this AND gate second time or create a copy second time. Call it A1 to differentiate between the first instance. Dot I0, again this input AND2 has I0 input, I1 input and O input. So what are they connected to? This I0 goes to I2, local I2 and 3 level I2 here. The second input of this second AND gate goes to temp. I1 goes to temp, is mapped to temp. It's called it is mapping to temp. Dot O, the output of the second AND gate goes as a final output O. Dot O goes to O here. End module. So what we have done here is we have instantiated this two input AND gate two times, created a local wire, and then created this bigger AND gate, three input AND gate using the smaller AND gate. This AND2 that we are instantiating here is this module, which is a separate Verilog file. Module AND3 will be a separate Verilog file. So you'll have AND2.v, .v is for Verilog, and 3.v. And both files have to be part of the project. So when you compile or when you synthesize this code, it knows AND2 means this module, second module. So this module and the logic is copied twice, and I make the appropriate connections and generate a bigger AND3 gate out of it. Any questions on this, how it is working?
Nope.
So this way of modeling is called structural modeling. We saw that using Verilog, there are two methods, structural modeling method and behavioral modeling method. Structural modeling means we are literally creating this structure using Verilog language. So this will be part of structural modeling. So we can create even bigger designs out of it as required. So using smaller designs, we can create bigger designs. Okay, so if you don't have questions, we'll stop here today, and then we will again talk again on Wednesday same time in that case. Okay.